So that's CPI. Just to mention, other things that you can get from performance instrumentation counters, you can get memory bus activity. So a CPU, depending on the architecture, may be directly connected to memory buses. You can look at the throughput on them. If you try this, so the sort of thing I like to do is I try to identify bottlenecks on the system if I've got a high CPI. Maybe I've saturated a memory bus. It turns out to be a lot of work to figure that out. Finding the counters for memory bus activity, that may not be so hard. You then have, I know how many transactions I'm doing, I know how many cache loads I'm doing. What's the maximum? That can take a bit of research because each processor is different. It might have a different speed memory bus. Just knowing getting the counters in this case might actually be the easy part. You then have to figure out what the maximum is for your architecture to know how close you are to it.
Exactly. I think you're finding out also that if you bind the particular process that you're interested in CPU 0, you're going to find this result. If you bind it somewhere else, you might find a very different result because the bus architecture are getting complex, they're crossbar, they're not symmetrical, right?
Yes, yeah.
And so, depending on where you bind your processes, you're going to find different numbers.
Well, actually, that's an interesting point, Rock, that we should have made too on the CPI discussion, which is CPI, many years ago when microprocessors were simpler beasts, basically just required 2 counters, right? Clock cycles and instruction cycles, and you just, you did the math and it was simple. But with the microprocessors we're shipping today, you actually sometimes need to look at multiple counters just to figure out CPI because, because the pipeline has multiple instruction units in it, and so you need to count you need to grab the instruction count from each of the instruction units within the pipeline to actually get accurate CPI. And one last note on this, and then we'll drop back to the memory, is fortunately some of the chip designers took sympathy. And like in the documentation for the Spark 64 processor that's currently used on the M-series Oracle servers, they actually tell you how to measure CPI on those microprocessors. They tell you which PIC counter events to program in order to get CPI. So they're starting to do a little bit better job with documentation for at least some of the higher order metrics.
Another thing that you can use performance instrumentation counters to measure is the L1, L2 cache miss rates for the on CPU level 1 and level 2 cache. You may have a level 3 cache as well, where there are a few things. Most CPUs will have these PICs. You can look at the ratio of how many hits you have to misses. There might be, say, 90% or 99%. That may not work so well because if you have, say, 1% of misses, that 1% can be so painful. So often we're looking at the number of misses and comparing that between workloads and systems. So anything to do with L1 and L2 caches as well, you turn to the PICs for. Another talking point I wanted to mention, Spark. On the Spark architecture on Solaris, you had tools like busstat and trapstat. So I didn't quite have to go to CPU stat and the PICs to examine what the I/O buses were doing. Busstat might have done that for me. Another thing, I'll write it here.
There you go.
Another thing that's quite useful to go to the PICs for is the what's happening inside the MMU, the memory management unit, because there might be workloads that are causing trouble there. There are actionable items if you're a developer and you know you've got a bad TLB, TSB hit rate, you can actually adjust the page size on many architectures. Yep. They're the translation look-aside buffer and translation storage buffer. They're parts of the MMU for translating virtual to physical addresses. It's just another part that can have performance impact. On
Spark, tends to be very hard to see.
And can be very hard to see. So yeah, Spark, you had trapstat, made it pretty easy to examine what's going on there. If you're on x86, it's CPU stat to find out what's going on with the TLB TSP, unless we fix the trapstat.
Right.
Another point I wanted to mention is if you're starting to use these a lot from, say, the CPU stat and CPU track tools, it's very handy to write a wrapper so that you can output the data and then wrap it in Perl or Oracle scripting and then produce the numbers. Often, a lot of developers don't have a fond idea of doing wrappers, we like to talk to the libraries directly. So, because you're using the proper interface. If I'm just wrapping the text output of one command, that text output may be unstable, and as that changes, it's breaking my script. It's also running an extra process that I may not need to do. I may be able to talk to the library directly and access this information. CPU stat and CPU track are the one exception to this. The man page even tells you to write wrappers for it.
Right.
The library itself, if you were to write library tools directly, it's libcpc. It's not, I mean, it's part of I wouldn't blame libcpc. It's difficult because there's not a lot of standards for it to use. So
it's cryptic by its nature.
It's cryptic by its nature.
It just is.
Yeah.
And a really good example of that, by the way, is the CoreStat tool. So CoreStat is a tool that a lot of folks with. It's freely downloadable. You can just Google CoreStat. It'll be easy to find.
Very important for CMT.
Very important for CMT, right? The T-series servers, also available for the M-series servers,
Okay.
because they're also.
Where do you download it from?
You can get it, well, I don't remember the
You
download.
Google
CoreStat
CoreStat.
and you'll find it, yeah. I forget the actual name of the website, but CoreStat is, as Brendan, it's a wrapper. It's a Perl script that uses CPU stat to program the hardware counters to figure out the utilization of the cores on either the UltraSpark T2, T2 Plus, or on the Spark 64, depending on which system you're on. And then it does the math for you to tell you what percentage of utilization those pipelines are seeing.
Yeah, because in CMT world, a system can be 25% from the OS perspective, but actually CoreStat will tell you, no, your cores are fully used. Or
sure, yeah, because you have
like
a number of threads, 8 threads associated with the core on CMT. Exactly right. So it tends to be a little bit more accurate to look at the CoreStat statistics and see the utilization.
CPUs.
Yeah, and that's a wrapper. That's a script.
Yep, that's a wrapper. As an aside, apart from being an unusual tool that encourages you to write wrappers, CPU stat and CPU track are also unusual in that they are, I think they're the only multi-threaded user bin stat tool I know of. So those guys are actually multi-threaded because they will create a thread per CPU and bind it per CPU. And the output is actually, they just output when they gather the information, and it just happens to print. That's why when you're looking at the output of CPU stat on multi-CPU systems, the output can get shuffled because the threads are just printing when they want.
Sure.
And,
Okay.
Sure.
so that's interesting.
You could run into something similar with dtrace, where you might have to sort on a column if you're pushing, because it's just going to generate based on when the probes fire and the
Yeah,
CPU
the
they
same
fire
thing
on.
with Analyzer and developer environments. I'm just going to draw up a diagram, so I'll get you guys to talk about that quickly.
Rock, you're probably more equipped to talk about Analyzer.
Analyzer is a tool that comes out with our compiler from the compiler group. It's layered on top of a few dtrace for kernel. You can analyze kernel profiles, actually. You can analyze user application, which when you start them under Analyzer, actually you use collect command.
Sure.
Or
To do
ER kernel.
profiles, yeah.
And the cool thing about this is you will actually be sampling your program call stack at regular interval. So you're just gathering a lot of information online. And then you do all your analysis, post-mortem. And it allows to visually look at what's going on, and then you filter down. You kind of say, okay, the program started, eventually I got into a point where I was utilizing a resource.
Right.
And I'm interested in this, so I'm going to cut from minute 5 to 10, I'm going to filter out everything, and then you start your drill down analysis, who was calling whom, what are the high CPU functions, et cetera, et cetera. So you do this with profile, let's say, just time-based profiling interrupts. Okay?
Right.
That gives you just where am
Every
I spending
millisecond,
time?
whatever, yeah.
The program was spending time in this thread on this CPU.
Just sampling the PC at
Yeah.
some fine-grained interval.
And in the context of here is the analyzer can also be used not just on pure time sampling, but you can do something based on any given CPC, any given those counters. You can use them to say, interrupt the CPU every 1,000 cache bits. And when you do this and gather the data in Analyzer, it will actually tell you what are the lines of code that are statistically giving you those cache misses. So it's a very powerful tool. The fact that you can do the postmortem filtering and, you know,
So you can actually go back and look at your source code and say, okay, I'm getting all these L2 cache misses as I'm doing, you know, maybe I'm doing pointer chasing inside a loop, or
Yeah.
maybe I'm hitting a big array,
Yeah.
or some large data segment, and then, you know, maybe look for optimizations there to try to reduce
Yeah,
that.
absolutely. And you can also even do that with Analyzer. You will be able to say, this is the function that is costing it, but it's also, you know, when it's being called, function A is your I cost function, but only when it's called by B. When it's called by C, it looks okay.
Right, right.
So that's a very powerful concept to do your performance analysis.
Cool, thanks. I want to finish with this diagram and then a couple of caveats that I thought of. Just also, if you don't know where to get started, try to map out the hardware architecture. I like to draw up functional diagrams. This is just generic. This may be completely wrong for your CPU type. So try and find a similar functional diagram for your CPU type, and then see which of these components CPU stat can give you visibility for. What I like to do for performance analysis is just look at the load for each component. If you've had no visibility until you don't know what's going on, look at the errors for each component. Look for bottlenecks for each component. So CPU stat can help out, well, the performance instrumentation counters, depending on your CPU, can usually help out with all of these components. Floating point unit, your level 1 cache, which may be split into an I cache and a D cache for instructions and data. The memory management unit for the TLB and TSB caches. The level 2 cache, or E cache, which sometimes is external, but often built into the chip these days.
Right.
You may have an L3 cache as well. The memory bus itself can often be measured, and I/O buses as well. Or CPU interconnects can be measured. So try and map out a functional diagram. Use this as a checklist to get information for each of these components if you're really wanting to understand why CPUs are hot. It'll take you a long time. CPU, going through the user manuals, running your own scripts, it could be weeks of work, but you will definitely see things that no one else is looking at and really get to the bottom of the problem.
And and just to kind of put this all in context, this isn't, the use of these tools doesn't fall within the 80 or 90 percentile of the performance problems that we tend to look at when we get engaged with customers. This falls more within the 10 percentile. So maybe 10% of the time we reach a point where we've used all the data made available to us through the higher order tools, and we've done everything we can do. Now it's time to do this to get the customer to that, you know, over that last time to get their performance expectations met.
Yeah, exactly. 2 caveats to finish with. If you're using CPU stat and CPU track, be aware of the sys modifier. When you're specifying events, you can say sys, and that will measure
The kernel.
The only things, yeah, only when the counters are in the kernel mode, correct?
Isn't it both kernel and user? Oh no.
There's sys or user, correct? No?
Yeah, there's sys or user. So
No, I thought there was sys and no sys.
Ah,
yeah, this.
yes.
Check your modifiers. The point of this is for and if you're getting confused by this, we get confused by this as well. The performance instrumentation counters will increment sometimes if they're configured for you both. Be aware of how you've applied them. I make this mistake sometimes where I'm running my script and I look at the output and it's like, this isn't what I'm expecting, there's so few events, yet I'm doing a very busy workload. As it turns out, I'm only measuring user land, I'm not measuring the kernel, or vice versa. So look at the modifier switches, it's in the NAM page for CPU stat. I got them inside my script, so I don't remember them, I don't program them that often. And the last caveat I can think of is naming the names of the cryptic counters themselves. If you type CPU stat -H and you see all those names, and you then go to the manufacturer's manual and look them up, they may not be the same. So the names that we put in CPU stat are things that the Solaris engineers have thought would be useful, but they're not the same things as what the Intel engineers call their counters, or may not be what the Spark engineers call their counters in AMD. What is consistent between them is the hexadecimal codes. So all of these events have a hexadecimal code. There's codes for the modifiers as well. I use that to try and translate between, it's like a Rosetta Stone to translate between the developer manuals and then what CPU stat is telling me on Solaris. And there's even a header file you can look up for them if you dig through the source code.
Right, and one more caveat that, Rock, you mentioned it early on, but I think it's important to mention it again, is the use of processor set and binding when you're using these tools. Because by definition, out of the box, every thread on the system is potentially going to be scheduled on any CPU, and if you're just looking at one particular processor thread, you're going to get a lot of noise in there. So what you want to do is start off, create a single CPU processor set, bind your target process to that set, and begin using these tools to look at that, keeping in mind that once you go from that sort of pristine environment of having my own CPU and potentially my own L1 cache and my own L2 cache to maybe the production environment where now it's shared, then the behavior is going to change.
It might be different. Yeah.
Might be very different. But.
No, and I think that's everything. I do want to stress again that the codes you put after the event modifiers can get really complex. So on some architectures, you have to specify a UMask, and then the UMask is another hexadecimal number that's used in conjunction with the event. They can often give you breakdowns of what types make up that main statistic. So it gets complicated. It gets really
but
complicated.
gathering those skills is possibly one of your very unemployment insurance.
That's right. The few people understand this. There's really not many people who have done a lot. Richard Smith has done some good presentations on CPC counters as well. But a good skill. It's very useful in some situations, as Jim said, and a rare skill, as Rock said.